morning, everyone. Before I begin this presentation, let me just remark on the organization, conceptual organization of the topics in the lecture and the progression. So we started with the first 2 days talking about the physical principles, foundations of heliophysics. And today is transition to what you might call observational heliophysics. On the topic of observational heliophysics, there are 3 lectures. You heard the first one, excellent presentation on in situ observations, measurements, techniques. And there are 2 others. The optical will be the first lecture in the afternoon, and the radio techniques is tomorrow morning. And the talk that I'm going to give is, you can think of it as the transition between observational heliophysics to the remaining topics, which has to do with data-driven heliophysics exploration and investigations. The observational heliophysics, again, links the physical principles to observables, the quantities that we can measure and then use to interpret the underlying physical processes. So that's where this lecture links, and as you can see, it's a lofty title, Overview of Data Analysis and Inverse Problems. Of course, overview it has to be, because it's a topic that there are even entire departments, thousands of textbooks on these topics. So I have to narrow the scope of what I'm going to talk about, and the guiding principles for me are some level of abstraction of, let's say, this type of principles that are agnostic of the type of measurements, let's say the domain of electromagnetics for the measurements. So with any abstraction, with the goal of abstracting things and talking about, for example, the inverse problems that appear in both optics and in situ, there's also caveats. And the caveat is that you have to go back and really look at the underlying assumptions in those observations, noise, uncertainties, in order to be able to apply the correct methodology. But I'm going to try to generalize as much as possible. Another thing that I should mention is, since I'm talking about data analysis, we really need to narrow the scope of what people refer to as data-driven scientific exploration. What you're looking at here is what's referred to as a data life cycle, starting from essentially acquisition. That's been the topic of or sensing, acquisition, measurements, how the data is generated. And so that's the topic of observational heliophysics. And that has to do with a representation, storage, retrieval, all of the arrows that you saw from, for example, measuring a current, and digitization, discretization, compression, storage, transmission, all of those types of things, okay? And then that goes into data analysis. Under data analysis, essentially we're talking about computational, mathematical, statistical, and algorithmic techniques for modeling high-dimensional data, and possibly unstructured. The topics that there are 3 lectures that I'll follow in the coming days will focus more on the ability for us to develop an automated ability to identify, recognize patterns in the scientific data, and perhaps infer some insights from those patterns. But today I'm only going to talk about how we take observational data and perhaps take it to the level where we can see very elementary patterns, not in an automated fashion, okay, in the context of inverse problems. And the final part has to do, again, with data sharing, collaboration, open science, the kinds of things that are very important, but I won't be talking about at all. So I'll focus only on the middle part, and only a subset of that. This is not moving. Is this something that I need to do? Okay, thanks. So just to give you an outline of the scope, I'll talk about a state space abstraction, essentially a mapping between physical parameters and observations. And the model that I'll use for that description is the integral equation and its equivalent, the interplay to differential equation models. I'll talk a little bit about the types of or categories of inverse problems and the related solutions. And I'll talk about what I'm referring to here as stationary inverse problem, which means that even though the quantity of interest that we are trying to infer, some, let's say, inferred physical parameter, is assumed to be stationary for the data that we are measuring. But there are cases in which that quantity is changing during the time of acquisition itself. So for that, we need to have not only a time-dependent data model, but a time-dependent for the actual physical parameters. And I'll probably brush on that a little bit. So what are some examples, just so that we are, even though this is an abstraction, we have some examples that we can think of. Of course, the previous presentation and the ones that will follow have great examples. So we talked about distribution functions as an example. So what's the general model? The model is, we're only talking about a mapping, okay, functional mapping, between a space. This is a vector space, let's say n-dimensional vector space, defined over the real line. It doesn't matter, it could be complex. And mapped to an observation space. Again, let's say it's an m-dimensional vector space, okay? So a set of vectors that are defined of some quantity. In this case, I'm assuming that we are already talking about finite dimensional representations as opposed to continuous representations. And this is just, the most general form is just a mapping. It's a function without assuming any form. And later on, we'll of course focus on the cases where it becomes linear and has some other desirable properties, translation invariance, those types of things. That, for example, are the basis of convolution, as an example of what we've already heard. So what are the examples? Let's say densities, velocities, temperatures, composition, electric fields. We have seen all of those. That's the example of a state, but I'm denoting here as X. And the spectrum, the Doppler spectrum distribution function, however you want to talk about the quantity that you are measuring and how you map it, the underlying physics of that measurement to the parameters. There were some talks this morning about people who work in ionospheric physics. Total electron content as measured using techniques of Faraday rotation or differential Doppler, and the electron density. So the electron density is the parameter of interest, total electron content is what's being measured, and there's a relationship between those two which has to do with essentially just a projection. You're projecting, which means that you're collapsing one dimension. You're integrating along some line of sight, but you can get that original three-dimensional quantity back using an inverse problem. So these are examples of what I'm talking about. In optical measurements, the quantity of interest may be a volume emission rate. And what you're measuring is a photometric brightness, could be polarized brightness. These are topics that will come up in the next lecture. But these are all examples of what we have seen so far. Now, one way to think about the connection between these parameters and the observations, this is the state observation abstraction. I want to essentially focus on the fact that we can model this input-output and the operator in between them as these three quantities, right? You have the set of physical parameters, you have the observables at the output, and there's a mapping, a forward mapping that goes between the two, connects the physical parameters to the observables, but what we measure is the observables, and so we need to go backwards and get the quantities, the physical parameters, okay? So in simulation, which is, again, a very important topic in many of the activities that goes on in the domain of heliophysics, the scenario is where we have initial conditions or boundary conditions and forcing parameters, and we generate simulated state parameters, and we do this by the numerical scientific computing techniques, finite difference, finite element, spectral methods, any of those types of methods. And typically they're computationally expensive, but there's also a challenge. The challenge is that the drivers or the boundary conditions themselves need to be inferred, typically from data, from observations. So sometimes even there is an implicit inverse problem in being able to specify those boundary conditions for the simulations. What's the first one? The first one is which is the focus of what I'm talking about today, is that given a set of observations and a forward model relating the state to the observations, determine the state parameters. And of course, the challenge that I'll talk about today is just because we have a forward mapping, it doesn't mean that we can easily go backwards. There are all issues in terms of understanding what is invertibility, what is observability, And so I'll talk about those. And what I'll talk about in the subsequent lectures, maybe you can think of it as learning, or in the language of, let's say, signal processing or control theory, it's usually referred to as system identification. What that means is that we have a set of essentially parameters that we are aware of, and then we have the corresponding measurements for those parameters. And when we want to learn the underlying functional mapping, in classical system identification, this is done by essentially the fact that we have multiple of these things, and we come up with a specific analytical or parametric underlying operator. We learn that. And in machine learning, really the difference between machine learning and classical system identification is the fact that this operator is not learned explicitly, but rather it is learned through some weight of composite nonlinear affine functions. Okay? That's the only major difference. Okay, so we have typically two of these quantities, and we want to get the third one depending on how we're setting up the problem, but sometimes we only have one. So there is such a thing as, for example, a blind deconvolution, in which case we only have the observations. We don't know the convolutional kernel, the instrument response function, and we don't know the input. So we have to also learn that. So that also falls into the category of learning. Okay, so the framework that I'm going to work with is based on an integral equation model of inverse problems. Now, of course, there's a history, long history of integral equations. One of probably most influential descriptions or frameworks developed early on, about 100 years ago. In fact, 102 years ago was the first publication of a treatise by Richard Courant and David Hilbert on a 2-volume book. The initial volume was based on lectures given by David Hilbert at the University of Göttingen, where Richard Courant was a student and essentially turned those lecture notes, wrote them, edited them. And this came out initially in German in 1924, 2 years before the Schrödinger's equations of wave mechanics. And soon after that, because of essentially the treatment of integral equations, operator theory, they became very influential because of their relevance to the topic of interest at that time. Later on, when Richard Courant moved to the US at NYU, the book got published in English, I think maybe in the 40s during World War II, and then another publishing in the 1950s. And it became a classic. So a lot of people working, and the title is, I think, Methods for Mathematical Physics. So many of you might have seen it or used it, but it's a really beautiful writing. In fact, when I mentioned this, Marco reminded me that Richard Courant has another book with a very humble title known as What is Mathematics? And it's a beautiful, beautiful book in really going back into conceptual underpinning of mathematical thinking. Okay, so that's just some interesting information, but getting back to how that's relevant to our discussion here, let me just again remind you that what we're talking about, x being the quantity of interest, for example, densities, velocities, temperatures, and so on. And y is the observed quantity. And the general case, which is nonlinear, is, as I stated, so you have this as a quantity observable as a function of time. The functional, the mapping is, I'm denoting it here by h, as a function of time, and some lag of those parameters because of the lag in the measurements. The nonlinear by additive, but additive is the case where, again, this is inside an integral when we are integrating with respect to that lag, either in time or space. And, but you can see that essentially the parameter is a function of the kernel inside the integral equation. And the linear observations, which is what I'll focus on almost entirely today, corresponds to the case where we have the observables. It's inside an integral with the quantity of interest times some kernel or Green's function, or depending on how you want to set it up. And in general, this is a function of two variables. So what that implies is that there is no assumption of translation invariance. Okay, in general, it could actually be different every time you move to different parts of, for example, a detector, CCD. At different locations, you would have a different instrument response or point spread functions. That's the most general form, but of course we can imagine that there is a linear version of it where that kernel is only a function of the difference. And that translation invariance, by the way, becomes important in the topic of discriminative models or supervised learning when we talk about deep neural networks, and in particular convolutional neural networks, because it really takes advantage of the fact that when you want to do, let's say, vision, computer vision or image recognition, you want to be able to recognize the same image independent of the displacement. And so that translation invariance becomes important. And this is what's typically referred to as a Fredholm integral equation of the first kind. If you look at tables of handbooks of mathematics, you'll see that there's essentially many categories of integral equations. Volterra equation, eigenvalue integral equations, but this is probably the most common one, okay? And I want to then maybe add a little bit to some examples so that we know what we're talking about. What is the integral equation and its corresponding differential equation model? So let's look at one example, and that's an inverse source problem. The problem is to determine source distribution from measured emitted radiation y. Okay, so it's essentially you have the following differential equation, and the k is given by essentially the wave number of emitted radiation. It's essentially a partial differential equation that has a corresponding integral equation, which can be written in a similar form with essentially the limits of integral along the radiative medium, where the kernel h is given by essentially an exponential that is decaying as a function of that radius. Okay? Another example is heat equation, or related to that diffusion equation, and this is now going in the reverse direction. What I mean by that is the problem here is to determine the initial state of what we are observing. So in other words, y of s at 0, meaning time 0, or x of s, the initial state from y of s at some later time, when the diffusion at some time has passed y. And we can write the corresponding integral equation, okay, as a function of s, spatial. This could be a spatial vector, three-dimensional, at time, which is integral of x and essentially a translation invariant in spatial form at a function of time. The kernel in that case is essentially something that looks like, you can recognize this. This looks like a Gaussian, the exponential that's raised to the square term and normalized by essentially time as a function of time. And the inverse problem is referred to as maybe a deblurring or deconvolution with, in this case, you have a Gaussian kernel. So the blur, the form of the blur, instead of, for example, an instrument response function can be square, rectangular, or circular, but in this case, we're talking about a Gaussian kernel. And you just have to deconvolve that. You have to essentially, from this measurement, y, obtain the quantity at time 0, what the source is. That's an example. There are many such models of integral equations and inverse problems. And of course, we've already seen some of these. When you talk about distribution functions, you have a spectrum, and then you have an integral, and then you have to go backwards. Deblurring, deconvolution, you can think of it as just about anything that you work on, has some element of an integral equation that needs to be inverted. In optical astronomy from ground, atmospheric turbulence, for example, can be modeled in terms of a corresponding kernel that, again, has the form of essentially the power spectrum of random fluctuations that you can model in terms of having some analytical approximation to that kernel. And if you can deconvolve that, you're essentially able to reduce the effect of the atmospheric turbulence in your imaging problems. This is probably the most familiar one to all of us, even though we may not have thought about it in this formulation. Everyone uses some form of harmonic analysis, right? We have a time series, we have some data, we want to look at the periodicities in it, and we use the method of Fourier transform. And in fact, in one of the earlier lectures, in the context of dipole versus multipole planetary magnetic environments, there was a discussion of, what was it? What was the method? Spherical harmonics, which is essentially, you can think of it as a 3D Fourier series expansion, looking at the harmonics. But what I want to remind you is that that model also has a corresponding integral equation. Okay? And it is described, you can describe the input-output relationship, the observed versus the quantity of interest, in the form of just a sum of these differential equations of arbitrary degree, k, with the corresponding coefficients. Okay, it's basically just essentially the ordinary differential equation model of arbitrary degree. But if you transform it, if you go through a transformation, let's say with a Laplace transform, what you do is that you convert this differential equation into an algebraic equation, right? It just becomes essentially multiplication of terms in that transform domain. And the corresponding integral equation is nothing other than just convolution. Okay? So convolution is one way of talking about this relationship in harmonic analysis. In the transform domain, you can think of it in terms of a Laplace transform, or in the discrete case, a Z transform. But does anyone know, or do you remember what allows us to, two things. One of them is, first of all, what does this convolution mean conceptually? What are we talking about when we talk about convolution? Not just as an operation, not just the mechanics of how we perform a convolution, but what does it mean? What is the implication of this representation? There are certain assumptions being made, right, to allow us to, given some instrument function, it was already discussed earlier today by Jasper, instrument response function in the case of 2D systems, a point spread function, the idea of how the instrument itself changes the original quantity as we are measuring with some sensor, right? That process. So that instrument response function, if we have that, what the statement of convolution is that we can essentially, for any arbitrary function, we can just represent it using that linear combination of that shifted versions of that response function, right? So the response function is what? Is typically represented in the continuous case with the Dirac delta function. And in the discrete case, it's a chronicle delta. But what's the statement? The statement is that as long as I know the response of my system to an impulse or a point disturbance, then any arbitrary input to that system, I can represent it as linear shifted versions of that impulse with the altitude. The amplitude is adjusted according to the value of the function. And therefore, that means that as long as I have this H, I'm able to obtain the output to that system. I can categorize. I can characterize it using that information, right? And so, of course, this is the meaning, the significance of convolution. And if you transform it using a certain type of basis function and compute the Fourier transform or Laplace transform more generally, then you convert this seemingly cumbersome operation of convolution into algebraic operations of multiplication and addition of terms. What allows us to do that? It is. Yeah, that's why I'm pausing. Why can we convert something that looks like a convolution to just essentially, once we take the Fourier transform of the of elements, the input and output, and the instrument response function, it just becomes multiplication, right, in the other domain. Why can't we do that? Perfect, perfect. They are orthogonal, and furthermore, so, okay, let me repeat what you just said. The basis function, so there's a basis expansion in the transformation, which is essentially given, in the case of Fourier transform, by complex exponentials, or sums of sines and cosines. These complex exponentials are eigenfunctions of linear and translation invariant systems. And what that means is that when a complex exponential goes in as the input to the system, at the output you get the complex exponential, except that maybe its amplitude and its phase may be altered by that h, that instrument response function. Okay? So because of that, now that allows us to essentially do this transformation into a space, a transformed space, where everything becomes essentially just multiplication and addition of terms. And that, of course, the implications of that are profound, because from a computational point of view, because we have fast algorithms such as fast Fourier transform to be able to perform this computation in the transform domain, we can essentially do things that, let's say, by late 1960s, before the rediscovery of the fast Fourier transform, we were not capable of doing that. But all of a sudden, by 1970, we were able to, all of this, what you see around you in terms of the digital revolution, this is really a foundational principle of why we can do that. And I mentioned, you noticed that I mentioned, I called it rediscovery of fast Fourier transform. Does anyone know why? Because it actually was first invented by Gauss about 150 years earlier. It's just that digital computers did not exist at the time. And he actually came up with the idea, and it took almost a decade after the reinvention of FFT, if you look it up, for the historians to trace back the original divide and conquer n log n algorithm to Gauss, because he was trying to compute trajectories of celestial bodies. There's a telescope actually in his house in Göttingen, so it's for his pastime. There's a chair there, still there, and a telescope we would be looking up. And observational astronomers couldn't find one of these comets, and asked him to calculate the trajectories, the orbits, and of course the computation at the time was very hard. So he had to come up with clever algorithms to be able to perform the computations efficiently by hand. So the FFT algorithm has actually a long history. So back to our business. What is another example of this general formulation? This is something that, again, has been discussed, reconstruction from projections. You can think of it as tomography. What does that mean? That means you have observables that are lower dimensional than the quantities of interest. You have one-dimensional line integrals, and you want to reconstruct a two-dimensional or three-dimensional quantity, or images two-dimensional, and you want to go to the third dimension. And what allows you to do that, to be able to actually solve this underdetermined problem, is the fact that you have measurement diversity. You have multiple perspectives or time or whatever that diversity might be that allows you to do that. But the model is essentially just a projection. You can write it, again, as an integral equation with the corresponding set of projections through that medium. And by the way, the reason I'm mentioning this is that this is not only in heliophysics, of course, it goes beyond all of our domains, but in radio astronomy, for example, phased array antennas, all the techniques of aperture synthesis, interferometry, they have their basis in essentially solving this inverse problem. Okay. All of those techniques have to do with solving this inverse problem. Okay. One other thing I want to mention before we talk about the solutions or hope for solutions of these types of problems, or how we go about formulating the solution of these inverse problems, is back to the sampling. The sampling was mentioned in the previous talk about the choice of, in that case, for example, how closely you you're scanning through your observations. Essentially, in that case, you wanted to sample the distribution function. And if the samples, consecutive samples, are too wide, you may miss some information. The sampling happens for both the parameters, x, because you have to represent it in some domain, right, that you can compute. For example, the pixels of an image that you're trying to reconstruct. But it also happens in the observation domain, in the data domain, right? And the data domain, that means, for example, if you have currents that you're measuring, eventually you have to discretize that somehow. That discretization, you can think of it as a basis expansion. The choice of that basis expansion has to do with, essentially, how you think of obtaining those samples. So it's not just only a uniform, necessarily non-overlapping sequence of samples. I mean, that's the standard one for which, again, the basis function is just what's known as a Haar function. It's just a rectangular basis function, and you sample through that function. But it doesn't have to be. We already talked about the exponential being one option for the basis expansion that we have into this expansion coefficients and the transformed domain, and then essentially working with the expansion coefficients in the transformed domain. The reason why I'm mentioning this specifically is because on the lecture on Saturday, when we talk about topics of exploratory data analysis, clustering, generalized classification types of problems, we will think about how to obtain these basis functions that are data-driven. They're not fixed bases, such as in sampling, these Haar functions, or in the case of transformation harmonic analysis, these complex exponentials, but they're actually adaptive basis functions. Okay, we'll talk about that on Saturday. Nevertheless, so if we do a discretization using this basis expansion, and then you can see that essentially you end up with a matrix vector representation of that integral equation. Okay. The left-hand side is the observations y. It doesn't matter what the dimension is. It can be, if it's two-dimensional or three-dimensional or n-dimensional, because you've all already done this in Python or MATLAB. Essentially, you can do an embedding of any higher dimensional function into a vector, as long as you just keep track of the lexicographic ordering of what they map to. And then, of course, the operator is in the form of a matrix, and the unknown parameter of interest, again, is a vector. Okay, so then we have a simple formulation of infinite dimensions. Let's say h is m by n. Those are the dimensions. In general, we don't have to have the same number of observations as unknowns. That's a more general case. If we did, it would be a square matrix, and we can talk about what the implications are. But essentially, it's just the sampling of that original integral equation. Okay, now, I'm going to forget about the integral equation. I'm just going to focus on this algebraic problem, because ultimately, when you go and you want to set up a problem of your own research and interest, that's how you solve it, right? You go in there, you have these vectors and matrices, and then you have to solve the problem. So what's the statement of the problem? Y is what you have, your measurement, your data, your observations. And you have a mapping, and of course the mapping of that h depends on the specific type of that integral equation that sets up the problem, what that is. And you want to solve for x. Okay, so that's basically the setup that I'm talking about right now. Notice a couple of things. First of all, I'm assuming that we have the full vector y or a fixed x. X is not, so this is not a function of time. Of course, you obtain the data over some time sequence, whether it's an integration of sequence of images or whatever it is. You obtain that, but you're assuming that x is your parameters of interest, physical parameters of interest, are fixed in time. They're not changing. But there are cases in which, during the time when you're acquiring your image, that may be changing, and then you have to take that into account. So that's the first case, is the simplified version of that. And second thing that I want to talk about is the non-trivial consideration that you have noise and you have uncertainties and you have all kinds of, as discussed before, it could be systematic errors and others. I think I mentioned that essentially in observations, there are two types of uncertainties, right? You have what's known as aleatoric uncertainties, which essentially means what cannot be reduced. In other words, it doesn't matter if you take more data, but you have to live with it. It's part of the measurement. What's an example of that? When you're making an optical measurement, your photon counting is an arrival process. It's a counting process modeled by Poisson distribution that is essentially a signal-dependent noise. For a fixed integration time, you have to live with that noise. It's part of the observation, right? You can take multiple measurements, or you can prolong the observations, but then you're changing the parameters of that Poisson distribution. But it's inherent in the observation. The example that I mentioned before is that if you flipping a coin, it's distributed according to a Bernoulli distribution, right? And it doesn't matter if you keep taking additional data, you still have that uncertainty. You have the model of uncertainty that's inherent in your observations. It cannot be reduced. Whereas the alternative, which is essentially the epistemic uncertainty, has to do with the fact that we can maybe either have additional samples of the observations or more observations, longer integration time, and reduce the error. But so the reason why I'm talking about this is that even though there is an advantage into this abstraction, generalizing things, simplifying, it's important to have a healthy skepticism and understanding of exactly how you should model the uncertainties and the noise in your system, because if you don't, it's very easy to get results that are meaningless, that become immediately hard to interpret or make sense of. So in the language of NASA, for example, there's a level 0 data, which is direct measurements that are through your telemetry are transmitted at the level of bits, okay? And then through calibration and certain assumptions of your detector models and other things, it goes to a level 1, which is typically calibrated. It's still raw data. And then level 2 is when essentially you get to what I'm talking about. There's an inversion or deconvolution or things of that are involved. And if you want to do that correctly, sometimes you have to go all the way to understand that the source, the bits, and the assumptions that went into the discretization, the resolution, the sampling, the errors and uncertainties, and the type of errors that make sense. For example, on a CCD detector, of course, for an optical measurement, you have the Poisson noise, but you also have the readout noise, you have thermal noise, you have the background noise, where you're not observing anything, and all of those need to be modeled and perhaps approximated by a simpler model, the way that I'm describing it here. I'm describing this by an additive noise. It could be modeled as a Gaussian if you can justify that approximation, but it's important to not just take it for granted and really verify. Trust by verify. If somebody gives you some data and say that this is how it can be modeled. Okay, here's an example of types of images in the model of essentially image reconstruction from projections that I talked about. So these are polarized brightness chronograph images. And you can essentially, as an example of the reconstruction from projection, you can relate these to electron density in the corona using the process known as Thomson scattering. And again, that has a corresponding integral equation. It can be discretized. I'm just going through this example to show you how you can go from this model, which is essentially this integral equation model, into, again, the matrix vector linear algebra problem. And then you can just stack these multiple observations and set up an inverse, an algebraic problem, and then the question becomes, okay, what do we do about solving it? You can see how you stack things up. Each one of these observations corresponds to, for example, one image, and you stack the images. You have the corresponding radiative transfer. It could be simple, depending on the specific problem, or it could be something that you need to perhaps make more approximations there, and some noise, and then you have to solve a problem of this form. Again, we are reducing it to something that we can all translate our own specific problems into this framework, and then now be concerned with what kinds of things do we need to be thinking about when we want to solve this problem. Incidentally, before I even go into the details of how we need to be thinking about these problems, how many people have had the occasion of solving something like that for some problem that involved data? Very simple. Numerically is what I'm talking about. And what's the typical way you solve it? You probably call a function in something in Python or MATLAB, but what is that function? Like how do you come up with a solution of such a problem like this? Meaning that this is your data, you have A, you don't have X, you have some model of noise. Yes? Least squares, very good. So a least squares solver, and okay. I'm going to talk about that and say when you can do that and when you have to be careful that that's not going to cut it for our problem. So that's you're kind of leading me to the next part, which is I want to talk about this perhaps a little bit more, let's say, concrete statement of this inverse problem. So the statement is given this y, and in this case we are focusing on linear operator. It doesn't have to be, but let's keep it simple. Find x such that this equality holds. And I talked about already, x being the object space where you look for a solution. Inherent in there has some sort of discretization or basis expansion of that quantity, physical quantity. And it also, even the choice of how we're going to do the basis expansion and sample x, as discussed before, has to have some notion of some a priori notion of where that solution resides. The example earlier was given was, I think, in response to a question about how do we know, how do we actually get parameters from these distribution functions? And the answer was that if we know the underlying medium, for example, helium and hydrogen and what the ratios should be, so that underlying assumption will allow us to figure out what sort of sampling or how fine a sampling we need to have to be able to resolve those things. So that's where you look for the answer, for the solutions, and then the data space. And in general, the observation space is a superset of the operator times the unknown. So can we talk about, what can we say about invertibility? And of course, this has a long history, at least in the sense that I'm talking about, goes back to Hadamard in 1915. And the notion of a well-posed inverse problem. So you hear, by the way, these terminology in the papers. People talk about an inverse problem is not well-posed, and but what does it really mean? And what kinds of things are potential issues? Well, according to Hadamard's definition, an inverse problem is well-posed when the solution exists, which means that there is for all observations y, there exists an x such as this equality holds. That means the solution does exist. Uniqueness implies that if you operate on two different physical parameters, that implies that the two are the same. Essentially, you have this one-to-one correspondence. And there is a third concept, which is not really about uniqueness and existence, but it's about the stability of the solution. Does anyone know what that might imply? What does it mean, solution stability? Yes? Exactly, yes? Converge. Well, convergence is a notion of, when you talk about convergence, you're talking about the sequential successive projections into hyperplanes, right? And so that really is a question of optimization of a solution, optimizing the solution in an iterative fashion. But I want to go back to the notion of perturbations in one space, the observation versus the parameters. How much perturbation in one gets amplified in the other. So you perturb the observation, how much do you actually perturb, how much of an error you're going to have in your solution? And that is a function of what quantity, what entity among these, yes. The noise is certainly something that can get amplified. the noise can get amplified. But the same noise might get amplified differently depending on the operator, right? So essentially, this operator, right, the mapping, the characteristics of that mapping, and in the case of continuous functions, it really has to do with the notion of continuity. The statement of that is that the y, your observations, have to be a continuous function of the input. So you don't have discontinuities and difficult problems. Otherwise, it becomes difficult to go back. Things get amplified, okay, because of noise. And in the finite dimensional case, the case where we are essentially solving these linear algebra problems, the existence, as mentioned already, is addressed by essentially, we don't have a solution. And what that means is that we need to settle for an approximation to that solution. And typically, that's done by least squares. Uniqueness is typically addressed by essentially the fact that we may have an infinitely feasible, admissible solutions, and you have to settle for one, and typically you go for the one with the lowest energy, a minimum norm solution. And stability is captured by essentially what you described in words, the notion of a condition number of a matrix. And that essentially tells you that amplification that that operator gives you, depending on the condition number, it's related to numerical rank. So for example, we know what the rank of a matrix is, but this numerical rank, what that means is that you can have, for example, rows or columns that are perhaps almost within some numerical range, linearly dependent. And therefore, you may have deficiencies that cause the amplification of your solutions. Okay, so let's talk a little bit more specifically about these conditions, the conditions of existence and uniqueness. Yes? Singularity of what? In the operator, you mean? Yes, absolutely. That's, in fact, it's related to something that I alluded to earlier about the fact that you can solve the convolution problem. If you want to do deconvolution, you want to go back to the source, you can do that algebraically, right? Algebraically means that if convolution implies the product of two things, deconvolution means division of two things, right? And that division in the numerator as a function of frequency, your frequency response, if it has nulls at some frequencies, those are points of singularities. You're dividing by those. And that exactly is another way of thinking about this issue that I'm talking about. So inverse filtering, if you will, which is what's referred to when you go backwards and you remove some distortions or blurs or those types of artifacts. You cannot just do it by just simple division, as I described to you in a conceptual fashion. You have to do something somewhat more sophisticated. Okay, so the exact solution implies that the null space of the operator only has the vector 0. What does that mean? Well, the null space is what? Is the set of all vectors that result in the 0 as a solution, as the output, right? So the implication is that the only set of input vectors that produces the 0 output is the vector 0 itself at the input, okay? And so what's the implication is that the mapping is injective or one-to-one. And in the case of our formulation, that means essentially full column rank, and that takes care of, that takes care of the uniqueness. The second one has to do with existence. The first one, the null space being 0, has to do with the uniqueness. The second one, existence, implies that the range of H is essentially the codomain, okay? The range of H is equals to Y. So the range of H is the codomain. And that means that the mapping is surjective, or onto, and that means we have the full row rank in the formulation that I described to you. So in this case, the only time you can have an exact solution is that the implication is that your matrix, your operator, is square and full rank. When do you get that? Never, unless you're solving homework problems, right? But you don't, with data you don't. So that's why it's important to be aware of the implications of such things. So the second case, the non-existence, which leads us to least squares problems, is when the range of H is a subset of the codomain. So mapping is not surjective. And it corresponds to in the linear algebra formulation in an overdetermined case, n degrees of freedom and m greater than n constraints. More equations than unknowns. Okay? So basically that's what we're talking about. That's when the solution doesn't exist. Non-uniqueness is when the null space of H is not just a zero vector instead of zero vector, mapping not injective, and that corresponds to the underdetermined case. Fewer equations than unknowns, too many degrees of freedoms, and then you end up with infinitely many solutions. So you have to kind of look at the operator and the mapping for your specific problem to figure out which one of these things makes sense. So now finally going to this non-existence business and least squares. Of course, we all solve some sort of least squares, use some solvers. It doesn't matter how you solve it, but what is the conceptual underpinning? What does it mean? We don't have a solution. That's the first thing. But we don't want to stop there. We want to come up with the next best approximation that we can get. And that next best approximation is defined in terms of some error vector, which has to do with essentially an orthogonal projection, finding the smallest error vector. Okay. Let me just briefly talk about notation because I'm going to use this notation for the remainder of today and also for the subsequent lectures on machine learning. The general L norm, which I'm going to write it as this L subscript, it just basically means you raise the elements of the vector to the power of L, the absolute values of that. You sum them all up and you take the Lth square root. Okay, not Lth root of for example, for the L2 norm, or essentially the Euclidean notion of distance norm, measure of length, the L2 norm is basically just squaring the elements of the vector, summing them up, taking the square root, and that's the usual measure of length. And in least squares, the idea is to find an x that minimizes the length of the error vector, okay, in this fashion. What's the idea is by the way, this notion, again, the notation I'm going to describe because I'm going to use it. Argmin means the argument, the x that minimizes essentially the quantity in front, as opposed to the minimum itself. I'm only interested in the argument that minimizes this error squared error, and that means what? The difference between y and an hx. And if I expand this in terms of an inner product, it's just the product of these two vectors, okay, the difference between y and the product. So how do I find the minimum? In this case, the problem is straightforward. You can just solve it analytically because all you do is just carry through the vector multiplication. You can minimize it by taking the partial, setting it to 0. Algebraically, you solve it with a few steps, and you end up with what's known as the set of normal equations. And your answer for least squares is just basically your operator transpose times h, compute the inverse, times h transpose, times your error vector. That gives you the least square solution. So you can solve it this way, and of course, you can solve it iteratively, which most solvers do, and I'll talk about that as well. Yes? Exactly. I'm actually going to talk exactly about that. Yeah, the simplest way to think about this actually is fitting some data, scattered data, to a line, the simplest thing, okay? And what is it that you do? Conceptually, what do? You are defining an error. The error is the distance. So first of all, you're finding that parametric model of line in terms of what? Two parameters, the slope and the intercept, right? So you have two parameters. And the problem that you're solving is that you want to search over the space of all possible intercepts and slopes such that the total squared error is minimum. And the squared error in that picture is, how is it defined? Just each element is what? The difference between what and what? Yeah, actual point and line. But is it the distance straight up or orthogonal to the line from that point? Which one? You understand what I'm asking? If I have these, if I have some data here, I'm going to say that this might be the line that minimizes the sum of the error, the difference between the scattered points and the line. But is the error this, or is the error this? When I add them all together, which one? The second one, the orthogonal, or the first one? Okay, see, even it's very straightforward, simple problem of least squares that we all use provide us an opportunity to think about it a little deeper. So the answer is, and I'll leave this as an exercise overnight for you to think about, is this, right? Because essentially, what is it that you're doing? You're not doing a projection. It's not an orthogonal projection. You're just looking at the values for that point, the x and y values of that line, and you're comparing it with essentially the equation of the line. So think about this, okay? Just think about this. And this is what you're minimizing. You're adding all of these errors, and then you do a search. You scan through all of the possible slopes and intercepts, and then you pick the one that gives you the smallest amount of error. But think about what I just said, because we all think that, okay, well, these squares, what's a big deal? But there's always a little bit of important stuff in there that we can think about that will add clarity in terms of how we use it correctly. Okay, so we solved this problem, and this has a very nice, simple solution, no problem. There is a related idea which is important because it connects us to the notion of understanding the uncertainties in our data, in our observations. And that's, for example, one framework in a deterministic setting is known as weighted least squares. What does that mean? That means that if the measurements are not equally reliable and we a priori have a sense of which measurements might be more reliable than others, we can attach weights to the errors and minimize a weighted error, not just E, but this W set of weights times the error vector. And all that does in terms of the machinery that I just talked about is really nothing. You just carry the W through, you end up with, again, the set of normal equations, except that you have this W transpose W that comes into the picture, okay? The same solution. However, the reason why I'm bringing this up is that, well, how do we choose these weights? Is there any intuition or guidance about how we should choose the weights? Well, that's the question, and the approach is there too. Determining the optimal weight, we can use the knowledge of average size or expected value of the errors and the moments of those errors. Variances, covariances and such, error covariances. How do we obtain those? Empirically. That's how we essentially obtain. And some notion of data covariance. That's how, that becomes, by the way, very important in machine learning modeling to understand those things, okay? So why, now, there's a connection between this and the particular distribution of the error, in particular Gaussian, and a connection between least squares and maximum likelihood that I want to elaborate on a little bit. Again, these are terms that I think almost all of us have heard or seen in some context. Least squares we all learned early on. Maximum likelihood, if you ever read an algorithmic solution to a problem, you have heard of maximum likelihood, you may even know how to formulate it, but the point I want to make is that there's a connection. There are different ways of talking about almost the same thing with some underlying assumptions. Okay, least squares, let me actually back up a little bit. So least squares, that sounds fine. If we don't have, so we use least squares if there's no solution, okay? And if there is not a unique minimizer, so in other words, we settle for a minimizer, a minimum, a minimizer solution, an X that minimizes the error. But if there isn't a unique one, then we pick one that has minimum norm. Okay, so that's known as minimum norm least square solution. Again, in some literature, people refer to it as a pseudo-inverse. You may have heard Moore Penrose pseudo-inverse. There are lots of different things talking about the same thing. All it means is least squares minimum norm solution, okay? In the way that I just described it. Now, there is a machinery that automatically gives you a minimum norm least square solution, and that machinery is known as singular value decomposition. Now, you may have come across it or not, but the idea of a singular value decomposition is just a generalization of eigenvalue, eigenvector decomposition. So you basically want to do an eigenvalue, eigenvector decomposition, but if you remember, eigenvalue, eigenvector decomposition only applies to square matrices, right? Now, but I'm talking about the n by n problem in general. That's why we talked about existence, uniqueness, all of those attributes. But if you generalize an eigenvalue, eigenvector, now instead of just having your eigenvectors that, with the similarity transformation that you have, now you have left eigenvectors and right eigenvectors. Essentially, that's because now you have two dimensions that are varying, and so the expansion is very similar to what we had before. Remember, for that operator gets expanded into these two matrices with a matrix that is diagonal, very similar to an eigenvalue diagonal element, but these two are not the same, right? In an eigenvalue, eigenvector decomposition, you only have these two to the left and to the right of sigma are the same matrix. One is transposed. But there are two, so that's the only thing because of the two dimensions, and he has some structure, but the idea is the same. Essentially, all that means is that you are doing this expansion of your singular values, okay? And you can find your solution, this SVD solution, which is just this inner product of the U with your data, and then times the V's and divided by sigma sub i's. The sigma sub i's are essentially related to they're related to eigenvalues, okay, with a square factor, essentially. Okay, so that's the solution, and the solution is guaranteed, you can show, to give us the minimum norm least squares solution. So it's least squares and minimum norm. It gives us, so it's a very nice attribute. So when you compute a pseudo-inverse in any of the environments, your favorite environment, and you compute that, that's what you're getting. In fact, you get a singular value decomposition, and you compute it in this fashion. You can, of course, compute it numerically efficiently. There are such algorithms for computing the SVD expansion, decomposition of the matrix. And that's the answer that you're getting, okay? Do you see any problems that you can anticipate? Because what I just told you is that, well, no problem. We don't have a solution, but we can get the best or the minimum error solution and the minimum norm solution using this machinery. Do you see any issues here? Yes? Exactly. So, I mean, you can see even just by the formulation of the solution that you have the singular values in the denominator. And of course, you remember eigenvalues, so you have large ones, and then when you order them, you end up with the small ones. But in the reconstruction of your solution, you're adding all of them. And so what happens is that when the singular values get smaller, they all contribute. That's okay if you have the exact, there's no noise. If you have a noiseless problem, it's not a problem, right? Because you're computing precisely. But the problem is when you actually have noise, because you get the exact solution as computed the same way, plus a term where that amplification of noise that has power, typically, if you think of white noise has power everywhere, but these, for smaller singular values, this grows, okay? That's amplification of the noise in your data. So what's this is a reflection of the ill conditioning of the problem, which I alluded to earlier, is about the stability of the solution. So what do we do in that case? First of all, what should we be aware of? What should we be aware of? If somebody says, well, I'm going to solve the least squares problem, here's my data. From a now pragmatic point of view, I'll pose this question. What is the caveat? What's the first thing that you need to think about before you just go ahead, march on and say that, well, okay, I'm going to solve the least squares problem. What do we need to pay attention to? It goes back to almost saying what I said earlier differently. Remember, I said, which one of these is responsible for this notion of instability in the solution? Well, somebody said noise, and I said noise plus the operator. So we have to pay attention about the conditioning of our operator. If you have an ill-conditioned problem, this is, by the way, this is different than ill-posed. Ill-posed has something to do with the notion of existence uniqueness, right? Conditioning has to do with what I was alluding to earlier, the notion of the stability of the solution. Perturbations in the observations, how much perturbation you get in your answers. Sometimes 1% perturbation can give you 3 orders of magnitude, and you end up getting bogus results. So that's one thing that we need to be aware of. Understand the conditioning of the problem. And the second, of course, is what are the characteristics and the magnitude of the noise. Whether you have systematics, random, how big, how small, because all of that plays a role into, if you just throw a noisy problem to a least square solver, you're going to get something, but that can be bogus, okay? The intuitive picture that I showed you in terms of a line fit to a scattered data, think of it in the following way. What if I have the scatter plot, but then I have outliers? What happens if I know a priori ahead of time that this is data, but then I have some outliers in my data? I'm saying that, assume that I know, because in general, I may not know which one is outlier and which one does. But if I do, what happens to the least square solution? It basically insists on fitting to noise, and that's exactly the issue with least squares. So you have to do something more sophisticated than just that. And this is something that comes up all the time. You know, people who work with data immediately, they experience this one way or another, depending on how much noise there is and what sort of conditioning of their operator they have. Okay, so that's the first thing to be aware of. Okay, that's fine. The notion of a, well, what do we do? In fact, before I talk about it, because I'm going to talk a little bit about what one can do about this. But what do, just by looking at this formulation, what is one thing that we can do, just intuitively, if nobody told you what approaches exist? Any ideas? Yes? Mm-hmm. Yes, 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 that certainly is an approach. We're going to talk about that. I'm going to talk about that when I talk about a little bit about the probabilistic formulation. But just looking at this expression, remember, what was the problem? The problem is smaller singular values, right? Yes?
If you don't have negatives, you can just add a constant to all of them.
Add what to all of them?
A constant value to all of them.
Yes, so I think if I understand the suggestion that you're giving is that accept the bias in your solution. Accept the bias to minimize the variance. You have the bias variance trade-off. So essentially, in that analogies that don't fit to the outliers, stay with fitting to the data. Ignore the outliers as much as possible to some degree, if you know that they are the outliers. That's the bias that you would accept. Is that more or less what you're getting at, or? Okay. So, but what about this? So, if you have an eigenvalue, eigenvector decomposition, and you want to get the original, not in the transformed space, not in this rotated space, but in the original space, if you want to get that back, what do? You go back and you reconstruct the space, one eigenvalue, one eigenvector at a time, right? You add them up, you multiply the eigenvector by the corresponding magnitude of the vector in the rotated space, and then you just add them up and you get the original back, right? But you don't need to use all of those vectors in your expanded transform domain. You can pick the large coefficients, the large eigenvalues, and neglect the problematic, the small eigenvalues. What's the trade-off? The trade-off is that now you are stabilizing the amplification due to small noise amplification due to small eigenvalues or singular values, but you don't have the reconstruction, the perfect reconstruction that would give you the inverse transform from the transformed space to the original. It's an approximation because you have eliminated some of the information, right? But that's the trade-off that you always make when you have noise in your observations. So you should always think about that we accept the bias by ignoring some of the small, not using some of the small eigenvalues. okay? But stabilizing so that we don't really fit to outliers entirely. That's the trade space. And of course, the immediate natural question is, well, how many of them should I eliminate? How many of them should I keep? Just like any question in these types of problems. And there's a host of different ways of thinking about that. And by the way, this is not the only formulation. This is just the standard, what's known as a generalized singular value decomposition, or truncated or filtered singular value decomposition. It's just one way of thinking about it more intuitively. You can solve these things iteratively, and it turns out, I'm just going to mention the significance of it without showing you the proof. The proof exists in many textbooks when you look at these numerical methods. There is the idea, a common approach. In fact, some of the least-square solvists use these methods, and I'm mentioning this because of its significance in machine learning and neural net models, layered perceptron, which we're going to talk about, multi-layered perceptron, deep nets. The idea is to use an iterative inversion of H, not just the matrix formulation that we talked about. Essentially, the reconstruction method implies that you have some initialization, and that initialization, again, may have implications depending on the form of optimization problem, the convexity, for example, of your cost function in your optimization. And so you may be sensitive to that initialization or not, depending on essentially the characteristics, convexity in particular, of your cost. And followed by cyclically projecting the initial guess onto these hyperplanes defined by the observation equations, one at a time. So you repeat that sequential refinement, and then until you reach convergence. It goes back to the notion of convergence that was mentioned earlier. And this is related to, by the way, you can see it. So you have the next value, you start with something, and then you have the notion of an error. You have a notion of error, and then projection into essentially the solution space. And then you have something called alpha. And by the way, alpha, so first of all, let me take a step back. This algorithm is just one form of what probably the most common. When you take a course on optimization theory, the first algorithm that you learn is what? What is it called? Gradient descent, some form of descent, gradient descent, projection descent, right? And this is a form of that, and in the machine learning community, that alpha, there's a term for it. What is that called? Learning rate. Learning rate, because essentially what that means is that how it goes back to similar things that we were talking about. If you're looking for, let's say, a peak in a function, in the previous example, it was a distribution function, but suppose you have this convex function and you're looking for the minimum. Depending on how you step through that function, if the jumps are too big, you may miss it. So, but if they're too small, then it takes a long time, many iterations before you converge. So that's the trade space, okay? And again, just so that you know, we don't have to go into the details, we can't afford the time, but there are methods where they pick this learning rate adaptively, depending on understanding how you're marching through that search space, and how we can do that. So places where, for example, the function value change is not very large, you can have bigger leaps, but then when you need to do the search where the slope of that gradient is large, you have to make your iterative steps smaller. But this is used a lot, and we're going to talk about that. Of course, this is the de facto algorithm for a lot of machine learning problems, right? There are two. There's a forward pass and there's a backward pass. And the backward pass uses a variation of this known as a stochastic gradient descent. Okay? And that's the most common thing that you use for optimizing for the weights of that function, universal function that we want to learn through a parameterized composite of nonlinear affine functions. Okay? But we're going to talk about that. I want to make connections so that when we see the new material, you'll remember that there's a connection with just solving the standard inverse problems. Okay, I think I have about, how much time do I have? 10, 15 minutes?
15 minutes, yes.
Okay, so for the remainder, I want to talk really about something that, again, we talked about a little bit of linear algebra. Now I'm going to talk a little bit of probability, again, at the undergraduate probability theory level, some of the concepts that are really foundations of a lot of machine learning that we're going to talk about later. Okay, so think of it as a little bit of review, but they're essential because we're going to be using them, and especially when we talk about generative models in machine learning. Okay, so what are the ingredients? There is a stochastic system that we formulate as the input being essentially a random process. By the way, when we talk about distribution functions, remember, it's a distribution. So inherently, we're talking about a probabilistic quantity, random vector, okay? Of course, we talk about moments of that random vector, and then eventually we work with quantities that are deterministic, but the underlying concept is that we're talking about distributions, right? Quantities. So there's a random process characterized by a probability density function. The output, again, also is a random process, and a description or mapping also is defined by a conditional density, a conditional probability. So this is, and now it becomes, instead of x, it's probability of x, that's the distribution. When I say a random process, I mean x is a function of time. At each instance in time, it's a random variable. So you have essentially a random process. You can talk about a random vector if instead of time, you have discrete, it's a sequence with function values. But essentially, at any fixed value in time, that quantity is drawn from a sample. It's a random variable. So we talk about the distribution of that P. A lot of times we don't have access to the full distribution, so we work with moments of that distribution. Then you have the output, but then the mapping is essentially specified by a conditional probability. That conditional probability is what? Probability of the observation conditioned on the input. So you can think of this as a probabilistic formulation of that forward map that we had as given by that kernel in the integral equation. Now that's the probabilistic formulation of that, which is just a conditional probability, okay? Now, what does that mean? By the way, this has a name, okay? It's a mapping. What is the probability that I observe y if I know what x is? What does that mean? That means that if I know what my unknown is, what sort of measurement would I get? If I know this is my parameter, physical parameter, what sort of measurement, change that for a different physical parameter, what sort of observation would I get? And think about going through this, all possible mappings that exist. And the name for this, again, I'm saying it because you have heard it, you have used it in some context. Does anyone know what this is called? Related, but not quite. It's simpler than posterior. It's the first step. The two are related using Bayes' theorem. This is a likelihood function. So basically, it's just when we talk about maximum likelihood, essentially you're maximizing this conditional probability. Okay, so okay, that's good. So what does it mean? Okay, a couple of concepts. Again, many of them you have heard, but we're going to talk about them a little bit more explicitly. So we have a system, a model of observation. That means that we have the input, which I already talked about. So what does that mean? We have a stochastic characterization of things such as temperature, density, composition, fields, those kinds of things. And we have some observed spectrum, also statistical quantity, stochastic quantity, and a forward model based on conditional density. So this is what I'm talking about. Now the inverse, solving the inverse problem in this probabilistic formulation, what does that mean? That means that I have an observation, again, underlying distribution, and I want to get the underlying distribution of the space, so I have to go backwards in terms of essentially getting the probability of x given y. This is what you were talking about, the posterior. So that's what that means. And these two are related through Bayes' theorem, okay? Now, that's just a formulation, but then there is an estimation rule. The estimation rule is similar to what in deterministic variational formulation of an inverse problem you would refer to as a cost function in the language of optimization, okay? The estimation rule, again, you define. You know, if you want a minimum mean squared error, you can show that that corresponds to the expected value of x of a conditional expectation, which is expectation of x given the observation y. So you have to solve for that. And it's not always easy to solve for that. And because it's not easy, what's commonly done for a lot of problems is, again, just like that line fit, you come up with something that's known LMMSE, which is a linear minimum mean squared error, a linear way of computing this expectation. And again, you can show that one of some of the classical solutions that you may come across that go back to maybe 40s, for example, a solution known as, in the context of adaptive filtering, known as a Wiener filter, that corresponds essentially to a linear minimum mean squared estimate. Just in case you come across them, sometimes you may see a paper where people present a result as if they use something new because the terminology is new to them. But if you really look closely, you realize that it's essentially a variation on the same approach. And the difference in performance, claimed performance, may only amount to the fact that they're using different parameterizations, different parameters, different tuning of results. So that's why it's important to be able to go back and make connections between these things. Okay, so, but there's another common and very important, this is probably one of the most important things to understand in a lot of these inverse problems, in the context of what people refer to as a Bayesian estimate. That's based on something known as the maximum a posteriori estimate, which talks about maximizing the distribution of the unknowns given y. And what is the expansion of this using Bayes' theorem? Anyone remember? The quantity inside the parentheses, how can I expand that? And as I mentioned, I can relate that to a likelihood that I showed you before. I can relate this x given y to y given x, but there's another factor. What is that factor? Like P of x, and there's a term, again, there's a term in statistical estimation theory. What does that refer to? Prior, exactly. So prior, what does that mean? That means that the distribution of the unknown that we are interested in, well, if that's going to come into the picture, what does that mean? We already know the distribution of what we want to solve for. So what does that really mean? That means that we don't really know the distribution, but we may know bounds on that distribution. We may know, for example, the fact that it is a subset of all possible distributions, or it's in a class of distributions, and that sort of information can allow us either implicitly or explicitly stabilize the problem exactly the way I talked about that deterministic variational form of solving the inverse problem, but conceiving it and formulating it in this fashion. So in fact, one of the things that we're going to talk about when we talk about generative machine learning, generative AI, is the notion of one class of such problems is that we want to be able to draw samples, okay? For example, let's just, in fact, there's an example that I think Andres showed you with a very beautiful artistic picture on a wave, right? That's an image, that's image generation problem. You're generating an image, how do you do that? You do that based on the fact that you have learned, presumably, an underlying unknown distribution, but an underlying distribution that could generate a class of such images. And you learn that by having access to a lot of other images of similar type, specified in a similar fashion. And then once you learn that underlying distribution, not explicitly, but assuming that I know what it is, sometimes, for example, you learn that distribution by transforming it into a space, a latent space. And we'll talk about all of this, but I'm just kind of letting you to look ahead a little bit. Once you have access to that, then you can just draw samples from that. You can generate new images that resemble all of the, or not resemble, but are related in a distributional sense to all of the previous images in that class. And by the way, this is the basis to a lot of what you may see as image-to-image translation or new formulations of super resolution. All of these kinds of techniques use the underlying principles that we're going to be talking about. Okay, so we talked about weighted least squares. It was mentioned before. I want to talk about the statistical interpretation of that. In particular, it turns out that the weighted least squares is no different than maximum likelihood as long as your model of the noise that drives the system is a Gaussian. So the statement is, so I'm going to set up the maximum likelihood problem. That means that I want to find an X that maximizes the likelihood, the probability of the observation given X. Essentially the most explainable forward mapping in a statistical sense. Okay, so if noise can be modeled as Gaussian, what's this conditional probability? Well, the conditional probability, and this has to do with the property of Gaussian distributions, and we have a linear model. Remember, y is equals hx plus some noise, right? If that noise is Gaussian distributed, now all we are doing is a linear function. We're just adding the operator times x to that, right? And that means that you end up with another Gaussian, because the linear function of a Gaussian is a Gaussian. That's a property of a Gaussian. The variance of that Gaussian is going to be, because it's conditional, in other words, I have fixed x, so the only probabilistic quantity here is y. So x, I fixed it, right? It's not random anymore. That means that the variance is essentially driven just by noise, not by the unknown. The variance of my resulting Gaussian. And the only thing that happens is that Gaussian gets shifted by, the mean of that Gaussian gets shifted by the amount of h times x. In other words, if I were to write this, of course, there's a constant outside of this exponential for the Gaussian, but the argument of Gaussian becomes essentially a product that looks like that the difference, you can think of it as mean shifted value. Remember, the form of a Gaussian, just a single Gaussian or a vector multivariate Gaussian. Shifted, the mean of the Gaussian gets shifted by the amount of hx, and then you have this quantity inverse of a covariance, inverse of the covariance of the error, that is equivalent to, well, let's see what it is. If instead of this, I can maximize the log of that quantity. And by the way, why can I do that? You know, I'm saying that if I want to maximize this quantity, this probability of y given x, I can equivalently maximize its log. What allows me to do that? There's an assumption. Close. Monotonic. It has to be monotone. So you cannot just go up and then come down again, right? So that's basically what allows you to be able to do this transformation in your optimization. And what that means is that now I can just essentially expand this in the way that I just described it to you. If I have this exponential, I'm just writing it in terms of a weighted norm, where those weights, the w's that I had before, now are given by the inverse of the covariances. Okay, so what does that mean? What that means is that, again, we solve the problem analytically by computing the partial, setting it equal to 0. And what we get, as before, is this essentially a weighted least squares problem where the weights are given by inverse of the covariances of the error. So if we know the error, we have some, in our measurement, we can characterize the error that gives us the answer to the question I raised earlier, which is there a systematic way to find the optimal weights in our weighted least squares? Well, the optimal weight, the maximum likelihood, tells you that as long as your error can be modeled as a Gaussian, you can approximate it as a Gaussian, then those weights are given by the inverse of the covariances. And by the way, what's special about Gaussian? Why are we, other than the fact that it's nice to work with because of these properties, right? But what's special about it in terms of the role it plays in nature? It's already been alluded to in a previous lecture yesterday in the context of kinetic models, particles, many particles. Yes? Okay, you said central limit theorem. Yes, exactly, but what is central limit theorem? Okay, so basically, I'll rephrase what you said. If you draw samples and you add them together, if you have enough of those samples that you add together, things begin to resemble like a bell-shaped curve if you add enough of them together. But there are some assumptions. Anybody remember what the assumptions are about the underlying samples, from what sort of distribution you have to draw them? Very good. What does that mean? Yeah, so see, the power of it is that it doesn't matter what those underlying distributions are. They can be anything, okay? They can be bizarre distributions, but as long as they're independent, so that when you repeat the experiment, it's an independent experiment when you draw samples, and as long as they're identically distributed, you don't jump around, things start in the asymptotic case. When you have infinite samples, it becomes Gaussian. In fact, the proof of central limit theorem, there are multiple ways, elegant ways of proving that, but the standard one is based on moment generating functions. So what you do is that you have the moment generating function of a Gaussian, then you have moment generating function of other distributions, as long as there are IID, and you look at the limiting case, when the samples go to infinity, it becomes the same as the moment generating function of a Gaussian. That's how you show that result. So there is a very important role here. That's not to say that we can always work with that. There are cases where it might be tricky. So we have to verify, first of all, if Gaussianity is valid, or if there is something we can do to... Actually, this was also alluded to. And I'm going to talk about it on Saturday in exploration when we talk about clustering, those concepts. You can use a Gaussian mixture model or a mixture of other fundamental distributions, and that mixture can capture a lot of exotic types of distributions that you may find in your data. So that's a powerful thing to do. But still, Gaussian mixture models, are based on essentially a linear combination of Gaussians, so Gaussians do play a fundamental role. Okay, I know I need to wrap up. Let me just say the final thing is that you can generalize this map, the maximum likelihood, to a case if you know something about your underlying distribution, okay? And you can do that formalism based on, I'll just show you the pattern of how the solution works out. If you assume, for example, in this case, that your underlying unknown is also Gaussian, if you know that, by the way, all that means is that you know the solution for the distribution, but you just don't know its width, and you don't know its height. You don't know essentially parameters of the Gaussian. Let's assume that that's the case. Of course, in most cases, that may not be, and so we have to think about how to represent that. But just for simplicity and for illustration, what a map estimate, maximum a posteriori estimate, means is that we maximize for vector x, for the unknowns, so that this posterior, as was mentioned before, probability is maximum, and this is the relationship in using Bayes' theorem. So the posterior is basically likelihood times prior, the product of those two. Okay, just look up the, and that product, what that means, again, we can write the conditional form. It turns out that that conditional is also going to be Gaussian with the following parameters. And if the prior is also Gaussian, again, this is a multivariate Gaussian vector, okay? So you end up with the determinant instead of just the division by the variance. But it's the same idea, and then you end up essentially with something that looks like essentially the maximum likelihood solution, or this term, plus another term. This term is referred to as a regularizer. This is what stabilizes your inverse problem solution, okay? So the theme that I'm going to stop here shortly, but the theme that you're going to remember in all of the subsequent lectures on machine learning is that we are going to need to stabilize the optimization problem for finding the weight of this universal function approximator that we are solving for using this gradient descent. We need to find the weights for this nonlinear composite of affine functions. And those weights need to be stabilized, and this general idea of the regularizing the problem this is one way to think about that. Okay, the fact that you end up with some notion of the prior in your solution, and that's what's known as a Bayesian estimate. And the final thing I'll say is that part of the advantage, a bonus of a probabilistic formulation, is that now inherent in the solutions, what comes out of the solutions is some estimate of your error. You can actually look at, for example, the covariance of your estimate. And if you look at the diagonal elements of the covariance of your estimate that you come up with, those diagonal elements are variances of your estimate. So what does that mean? If they're Gaussian, you can map them to confidence intervals in your reconstruction. So you end up with essentially quantifying how good your estimate is. So that's the added bonus that it gives you. Okay, so we're out of time. Let me pause here, but we'll have opportunity to revisit and expand on some of these concepts in the coming days. Thank you.
Questions for Farzad?
I guess I'm missing something. Can we get to bias theorem? Just
Yes.
shouldn't there be something in denominator like P of X? I mean, I don't remember exactly.
Yes, you're correct. The reason I'm not including that, the normalization in the Bayes theorem, is because we are optimizing for X. That's in the denominator, it's not a function of X. So I'm just, this is what you're talking about. Let me go back. Basically here, you're saying,
Oh, no, then it should
here,
be
here you're talking about, right? Here.
P of Y.
Going from here to here, right? Is that what you're getting at? Yeah.
Yeah.
So there's a P of Y, but I'm only maximizing with respect to X.
Oh.
So it doesn't matter in the maximization. Yes, if you want the exact form, you're correct. This is not the complete form of Bayes theorem. Thanks for catching that. I kind of just jumped over that. The reason I'm not including it here is because I'm only interested in maximizing with respect to X.
Other questions for Farzad? And or leftover questions, before I come to you, Doug, and any leftover questions for Jasper? Pass that over to David. Sure.
So I wrote it down. Yeah, it was sort of abstract question. So for from perspective of someone creating the instruments, what is the best point at which scientists that I want to use this data need to sort of contact you for some caveats of your data and instruments? What is the best point from sort of your perspective?
So are you asking when in the project you should contact people who know the gory details of the data sets and the instruments?
Yeah, just from your perspective, like someone who created these data sets and instruments.
So personally, I love it when people come and contact me at any point when they're doing a project, because I like doing science and I like talking about whatever cool problems you're doing. But I think what you're really asking is, when are you going to get the most bang for your buck? And so I would say that when you've sort of gone far enough in the problem to understand the problem that you're trying to solve, and you're starting to dig into the data and figure out the right models and tools to analyze it, but before you do your kind of final glorious computation, whatever that is, that's probably the right time to talk to someone who can just give you some tips about, okay, here are the places where you can really trust these values. Here are the places where you need to have a little bit more skepticism. If you're doing some kind of, weighted least squares things, here's where you have to be really careful about getting the right weights, these kind of things. So I think at a stage where you're kind of, not just starting out, you've really explored the problem, but before you really turn the screws on the computation.
Thank you.
So what is the nature of electrons and ions in solar wind with respect to its distribution function? I mean, how are they distributed in solar wind? Electrons and ions.
Okay, I'm not sure exactly what the thrust of this question is, but the answer is a common one in space plasmas, which is that the ions are essentially supersonic, which means that their bulk velocity is bigger than their thermal velocity, whereas the electrons are the other way around. Because their mass is so much smaller, they tend to be dominated by thermal velocity. So in terms of a distribution, the ions have a very narrow distribution that is offset from the origin, whereas the electrons have a very broad distribution that crosses the origin.
Okay.
And this is a very common situation in space plasmas, but it's particularly acute in the solar wind.
Okay, so this is what I wanted to ask. I mean, I understood now. So for electrons, the distribution function looks like broadband, in a sense that the thermal distribution is broader. I mean, with a broader thermal distribution, whereas in case of ions, the thermal distribution is, I mean, the thermal velocity is smaller, and thus we will see a spike.
That's
in the
exactly
distribution
right.
for solar wind.
Yeah.
And the reason is?
And yes, there's an excellent reason for this, which is that the temperatures of the electrons and ions tend to be not the same, but related to each other. And so if you calculate the average energy from the temperature, there's a 1 over square root of m in there. And so when you calculate, things like thermal velocities, because the electrons are 1,800 times lighter, that means that their thermal velocities are very, very roughly speaking going to be 40 times bigger than the thermal velocities of the ions. So broad distribution for electrons.
But this is not the case in case of magnetosphere, right?
It is not as exacerbated in magnetospheres typically because the medium is not flowing supersonically all the time like it is in the solar wind.
Okay, so this is the difference with, like, this is the reason why we are not observing similar kind of distribution in solar wind and magnetosphere, and therefore we need different types of instruments in order to detect these distributions in solar wind and in magnetosphere, right?
100% right. Yeah, in the solar wind, you can often get away with a narrow aperture for the ions because most of them are going pretty much the same direction. In the magnetosphere, they're going every which way. Broader aperture, and you need to sample ideally 4 pi, but as close to that as you can get.
Thank you so much.
Okay, so say you have something like a solid state detector where stuff goes in and knocks something out, and you're looking at a mission that's 2 years old, and you look at statistics, and you're looking at day 1 and day 400. Is there some kind of saturation effect that affects the data?
Oh, it's a beautiful question. Yeah, I mean, so the instrument that you calibrate in your lab is not necessarily the same as the instrument when it's 20 years into its mission, because detectors are made out of real materials and real materials age as they are used. So yes, absolutely, the characteristics of your detector may change over time. And if you're lucky, you can figure out, some kind of clever method to calibrate out that change in flight. But certainly, yes, that can happen.
I have a question that maybe connects both talks. So Farzad, in the last part of your talk, you mentioned how if we model the errors as Gaussian, then there's a really neat convenient way to factor that in. And so my first question for Jasper is that a reasonable assumption, or are there other maybe known distributions for the errors for certain types of instruments? And if that's the case, back to Farzad, is there a formalism that can account for other distributions of errors that's maybe not equally simple, but we can reasonably work with it analytically and computationally.
You want to start first?
You want me to start? Okay. I mean, yes, Gaussian errors are often a very good approximation, especially for what I do where you're counting particles. It's exactly this kind of, independent sampling of individual particles. And so Gaussian errors is a great approximation. I can say that there's a couple of problems that I'm working on right now where I have found that this breaks down, and that's when you're talking about very small numbers of counts. So when you have a distribution that has a lot of values that are 0 counts, what error do you put on those values? And this is a surprisingly tough problem to deal with, and maybe Farzad knows the answer, but...
So, just to follow directly from the comment, counting processes, when you're counting individual, whatever that may be, you could be counting the number of people showing up in the next 2 hours and at this door. Whenever you model a counting process, the distribution that's used for that is a Poisson distribution. That applies to any count of statistics, including detectors or photon counts. There's a result that you can show easily that when the arrival time mean of a Poisson distribution gets large, you can well approximate the Poisson distribution with a Gaussian. And that number is not actually that large. By the time you have an essentially count of about 10, you start seeing a Poisson distribution starts to look like a Gaussian. Of course, if you have more, it resembles that more. So having said that, that means that, for example, in instruments where detector counts things, as long as you have reasonable count for the duration of the time that you're adding, integrating those, then you can, first of all, you can verify. You can always verify. You don't have to make these assumptions. The most important thing, in my opinion, is to understand the characteristics of your noise. So, for example, in optical measurements, you have a detector that may have, first of all, an offset background. So that, when there is no incident photons, you still are getting to get some reading on the current on the detector. Okay? Every time you read out, you have a readout noise that can be modeled by Gaussian, but it's added to the signal-dependent photon statistics. You can have all kinds of distortions that could be systematic on your detector. You can have hot pixels, things like that. That again, if you understand, you can model that and you can say something about the distribution of your error, in which case, I mean, everything that I said actually can be generalized. The implication is sometimes it's harder to come up with a very neat analytical form of the site constraint in your optimization problem. It boils down to the fact that you have to solve a different optimization problem. In fact, in machine learning, what people refer to as physics-informed neural nets. We'll talk about that a little bit. All that means is that I'm going to make my constraint based on whatever assumptions I make about either underlying physics or underlying sensing process, my errors, whatever it is, I'm just going to constrain the space for which I look for a solution. So you can do that. The implications are you just have to numerically, in terms of how you do that search, you solve that optimization problem, it changes. Sometimes changes meaning that it becomes difficult to find the minimum, right? End up with things that are not so easy to minimize. Get a global minimum, for example.
Thank you.